Welcome to the deep dive. Today we're doing something a little different.
Okay.
Something you might even call elemental.
Okay.
Diving into the world of particle physics.
Ooh.
Don't worry, you don't need a PhD to follow along because
Right.
we're after something bigger. How scientists search for clues when they don't even know the full picture of what they're looking for.
And where better to start than with a paper on something called Dimension-8, SMFT coefficients. Buckle up,
Okay.
because it sounds like we're in for a wild ride.
I'll bite.
Dimension-8,
Yeah.
SMFT coefficients.
You're already speaking my language. Ha ha.
Mm.
Seriously, though.
Yeah.
Where do we even begin to unpack this? What's the mystery we're trying to solve?
Imagine the universe is sending us a secret message, a code hidden within the very fabric of reality.
Okay.
The standard model of particle physics, that's like our current code book.
Okay.
It's done a great job so far,
Yeah.
explaining a lot about the fundamental building blocks of the universe.
Right. Like the periodic table, but for the tiniest things imaginable.
Exactly. But here's the thing. We've started to pick up on some weird signals, like static in the cosmic broadcast.
Okay.
These signals suggest there might be more to the code than we currently understand. New particles, new forces, a whole hidden layer of reality.
Okay, so that's where this new physics everyone keeps talking about comes in. But how do we even begin to look for something when we don't know what it is?
That's where SMEFT comes in. It stands for Standard Model Effective Field Theory.
Okay.
It's like enhancing our code book by looking for patterns in the static.
Okay.
Those subtle distortions caused by these potentially heavier, undiscovered particles.
Mm-hmm.
Think of it like this.
Okay.
Imagine you're trying to understand a conversation happening on the other side of a wall.
Okay.
You might not be able to see the speakers,
Right.
but you can listen for muffled voices,
Yeah.
the rhythm of their speech,
Mm-hmm.
maybe even the occasional word that slips through.
So instead of searching for the speakers themselves, those elusive new particles, we're analyzing their impact on the conversation,
Yes,
the way they're subtly changing the words we can hear.
exactly.
That's actually brilliant.
It's a bit like being a detective at a crime scene where the culprit vanished,
Right.
but they left traces behind.
Okay.
And just like detectives need ways to analyze fingerprints or DNA,
Yeah.
physicists need tools to analyze these subtle fingerprints of new physics.
Okay.
That brings us to the Dimension-8 part.
Okay.
This refers to the complexity of those interactions we're trying to analyze.
Okay.
The higher the dimension,
Yeah.
the fainter those fingerprints are,
Okay.
but also the more they might reveal.
So it's like we're trying to pick out a faint whisper in a crowded room.
Yeah,
The fainter the whisper,
yeah.
the more sensitive our equipment needs to be to even detect it, let alone understand it.
Exactly. And that's what makes the paper we're diving into so fascinating.
Okay.
A team of physicists,
Yeah.
Upalaparna Banerjee, Joydeep Chakraborty,
Okay.
and their colleagues,
Yeah.
have essentially created a more powerful microphone for listening to those whispers of new physics,
Okay.
focusing on these Dimension-8 effects.
So they're giving us a sharper lens to peer into the universe's hidden dimensions.
Yeah.
Now, how exactly does their research help us decode these subtle signals?
One key concept is integrating out,
Okay.
which sounds complicated, but is actually pretty intuitive.
Okay.
Imagine trying to describe a complex machine.
Okay.
You could list out every single gear and spring,
Yeah.
or you could just say,
Yeah.
this part makes the wheels turn.
Right.
Integrating out is like focusing on what the machine does,
Oh.
rather than getting bogged down in the tiniest details of how it does it.
So instead of trying to describe these hypothetical heavy particles directly, which we haven't even discovered yet,
Yeah.
they're representing their effects on the universe in a more elegant, simplified way.
Precisely. It's like finding a mysterious note.
Okay.
You might not know the sender, but you can analyze the handwriting and the message to start piecing together who they might be.
That's a fantastic analogy. So by integrating out these heavy particles,
Yeah.
physicists can create a more streamlined model that still captures their essential influence on the universe.
Yes.
What else makes this paper and its findings so groundbreaking?
Well, they've also tackled a crucial challenge in building these effective field theories,
Oh.
removing redundancies.
Okay.
It's like when you're trying to solve a puzzle
Right.
and you realize you've been trying to force the same piece into the wrong spot.
Yeah.
You need to take a step back and make sure you're not misinterpreting the clues.
So it's about making sure our cosmic code-breaking system is as clean and precise as possible.
Exactly. The researchers emphasize the difference between equations of motion and field redefinitions.
Okay.
Subtle but significant distinctions that ensure they're not getting fooled by mathematical illusions.
Right.
They want to be sure they're seeing real patterns in the universe's static, not
Yeah.
just artifacts of their own calculations.
It's like making sure your telescope is calibrated correctly before you start mapping the stars.
Yeah.
Speaking of mapping the stars,
Uh-huh.
this paper isn't just theoretical stargazing, is it?
Right.
They actually apply these ideas to specific scenarios.
Absolutely.
Yeah.
And to understand their approach,
Okay.
let's look at one intriguing example they explore.
Okay.
The real triplet scalar.
Okay.
Don't let the name scare you.
Okay.
It's just a fancy way of describing a hypothetical new particle.
Okay, so let's break it down.
Yeah.
What makes this real triplet scalar so special?
Okay.
And how does it fit into their framework?
Imagine a particle as a tiny spinning top.
Okay.
Now imagine a top that's just floating there,
Okay.
not spinning at all. That's closer to what we mean by a scalar particle.
Okay.
It doesn't have the same kind of angular momentum as other particles.
Right.
Now this real triplet scalar is a specific type of scalar particle that
Okay.
theoretically
Mhm.
could interact with the known particles of the standard model in unique ways.
Okay, so it's like this real triplet scalar is a new character in our particle physics play.
Yes.
And by using their framework, they can predict how this new character might interact with the rest of the cast on the stage.
Exactly. And in this particular case,
Okay.
the paper shows how this real triplet scalar, if it exists,
Yeah.
could leave its subtle fingerprints on the interactions between particles we can observe.
Okay.
These fingerprints are those Dimension-8 effects we've been talking about, like finding an extra set of footprints at a crime scene, hinting at the presence of someone we haven't met yet.
So even though we might not be able to see this real triplet scalar directly,
Right.
we can look for the ripples it creates in the universe's fabric.
Yes,
It's like trying to understand the wind by watching how it moves the leaves on a tree.
that's a great analogy.
Yeah.
And that's the power of effective field theories.
Yeah.
They allow us to make predictions and test our understanding of the universe,
Right.
even when we're dealing with things we can't see or haven't discovered yet.
It's like those mystery novels where you have to identify the culprit based on clues and deductions,
Yeah.
building a case based on circumstantial evidence.
Yeah.
Now, I understand they didn't just stop at the real triplet scalar, did they?
Right.
They explored other particle models as well.
They did. They touched upon other scenarios,
Okay.
each with its own unique set of potential fingerprints.
Okay.
Like the complex triplet scalar,
Yeah.
the 2 Higgs doublet model,
Okay.
even something called a scalar leptoquark.
Okay.
Don't let the names intimidate you.
Ah.
The key takeaway is that they've created a framework flexible enough to investigate a whole range of potential new physics candidates.
Okay, so they're not just giving us a magnifying glass to look for clues.
Right.
They're giving us a whole detective kit. Now, with all these potential clues, how do we even begin to make sense of them? It's like drinking from a fire hose of particle physics.
That's where another crucial aspect of their work comes in.
Okay.
Categorization.
Okay.
Imagine a detective with a bulletin board covered in photos, maps, and red string. They need a system to organize those clues,
Right.
to see the connections and patterns.
So it's not enough to just gather the clues. You have to
Yeah.
arrange them in a meaningful way.
Right.
It's like creating a story from a jumbled box of puzzle pieces.
Precisely. And that's what this categorization allows physicists to do.
Okay.
By analyzing the specific types of Dimension-8 effects that each model predicts,
Yeah.
they can start to sort these models into different categories based on how they'd manifest in the universe.
So it's like sorting our suspects by their MOs, right?
Exactly.
If we know one type of particle interaction tends to leave behind a certain kind of cosmic fingerprint,
Right.
we can start narrowing down which suspects are most likely responsible.
Precisely. It's all about using these categories to make sense of the data we're getting from experiments.
Okay.
The paper focuses on 3 main categories.
Okay.
Electroweak precision observables,
Okay.
Higgs, signal strength measurements,
Okay.
and vector boson scattering measurements.
Okay.
Think of these as different types of magnifying glasses, each revealing a different aspect of those subtle particle interactions.
Okay, so instead of just looking at the overall picture,
Yeah.
we're zooming in on specific details, looking for those telltale signs that point to one new physics scenario over another.
Precisely.
Yeah.
And by comparing the predictions of different models to the actual data collected from experiments like the Large Hadron Collider,
Okay.
physicists can start to rule out some possibilities
Yeah.
and home in on the most promising candidates.
It's like comparing our theoretical fingerprints to those we dusted for at the crime scene. We're
Right.
not just looking for any match.
Yeah,
We're looking for a perfect match,
exactly. And while we haven't found that perfect match yet,
right?
this paper gives us a more powerful set of tools for analyzing the clues and building the case for new physics.
Okay.
It's a reminder that even though we've come a long way in understanding the universe,
Yeah.
there are still mysteries out there waiting to be unraveled.
Mysteries that might just rewrite our understanding of the universe as we know it. It's incredible to think that something as seemingly abstract as a Dimension-8 SMEFT coefficient could hold the key to unlocking such profound secrets.
It really highlights the power of human curiosity and ingenuity.
Yeah.
We're constantly pushing the boundaries of knowledge, developing new tools and techniques to explore the universe in ever greater detail.
Right.
And who knows what incredible discoveries await us just beyond the horizon of our current understanding.
It makes you wonder what other cosmic codes are out there hidden in plain sight just waiting for us to crack them. Maybe that's a question for another deep dive. For now, I think we've certainly given our listeners a lot to ponder. So until next time, keep exploring, keep asking questions, and keep diving deep into the wonders of the universe.